Okay, I'm going to do a couple of videos on different applications of DEs because they're just so important, and we do them all the time. And so we really need to know how to be good applications of DEs. Okay, I'll start with a couple of simple ones. I want to say simple, they're not very simple, but really good to know firstly how to deal with this. And so you might get, the first case that you might get is you might say that so y increases at a rate proportional to y or something like that. So y increases at a rate proportional to y. And we just want to know how to sort of convert that into a DE. Okay, and the second one might be something similar. It might be t increases, or let's say decreases at a rate inversely proportional to itself, or something like that. Okay. Okay, so let's just have a look at each of these situations. So y increases at a rate. Okay, so the rate that y is increasing by is dy by, we don't know what the other variable is, but let's say it's dy by dx. So the rate at which y is increasing is dy dx, the derivative of y. Okay, and that's proportional to y. And so the symbol for proportional is that the rate at which y is increasing is proportional to the value of y itself. And what this implies is that dy by dx equals some constant times y. Okay, and because it's increasing, this needs to be positive, and so we'll say that k is, it's increasing, so k will be greater than 0. And so that's how we set up this DE here. This is the DE that we've set up from this sentence. Y is increasing at a rate, so the rate that y is increasing is proportional to, so some constant k, where k is just some real number k, times y. Okay, let's have a look at the second one. T decreases. So what this is saying is the rate of dt with respect to some other variable x. Okay, dt dx. The rate that t's rate is decreasing, so it's proportional to, inversely proportional to itself. So what that means, it'll be 1 over t. The rate that dt dx, so the rate of t's change, is proportional or inversely proportional to itself. And what this gives us is that dt dx is equal to k over t. Okay. Now, because t is decreasing, that means that this number up here should be negative. And so what we'll get is k will be less than 0 for some real k. Okay, because it's decreasing, the rate is going down. It's going downwards, so this derivative will need to be negative, so k will need to be negative. The other way you could also write that is negative k over t, where k is greater than 0. You could also write it like that. The reason that's helpful is it helps out with your logs sometimes when you've got modulus and that sort of thing. It's nice to have something that's positive rather than dealing with something that's negative. Okay, so that's just a bit about how to set up your DEs. It's really important to know how to set them up. What I'm going to do is just go into my first example, where I'll just crack on. So the population of, let's say rabbits increases at a rate proportional to the population. Population itself. Okay, if the rabbit population, I'm just going to write pop if that's okay, is 200 when times equal to 0 and 1000 when time equals 10, and I'll just say years. Okay, so all time will be in years for this question. Find an equation that models the population growth. Okay. Of rabbits. Okay, so let's have a look at this. Hope I don't go over one page. It might go over one page. Populations. So let's just say P is a population. P is the population of rabbits, and we'll say that T is time, and that's in years. Okay, so let's have a look at what this equation will be. Population of rabbits increases at a rate proportional to the population itself. In other words, the rate of change of population with respect to time is proportional to the population itself. And this gives us dP dt is equal to Kp, where K is greater than 0. Why is K greater than 0? Because it's increasing. It increases at a rate. So this is getting bigger. The gradient of the curve is going upwards, a positive gradient. So there we go. So all we need to do is solve that dE. So let's do that. It's a function of P here, and so this is not helpful. We need to flip it upside down. And so therefore, dt on dP is equal to 1 over Kp. We flip it upside down. And to solve this, now that we have P on the bottom line here and it's a function of P, we can solve that T is equal to the integral of 1 over Kp dP, which is equal to, we'll take that 1k out the front, 1k log E modulus P plus C. There we go, that's what T is equal to. Alright, now, it's always good to, when you're solving DEs, to make sure you're aware of your initial conditions, your two conditions. So the two conditions we get here is when time's equal to 0, the populations is 200. So that'll be 0, 200. Okay, and 1000 when time's equal to 10. So when time's equal to 10, we've got 1000. Okay, so they're the two. Do you think it would be more helpful to substitute those in now or later? Now the population there is 200, so you're going to get a log E 200 and equal to 0. So you could do it there, that would work out not too bad. But this one here would be fairly horrible. And what I'm going to do is just wait until the end. You'll see that whenever you're doing these log E's and that, so this initial condition when your independent variable is equal to 0, that's much nicer to solve at the end. I'm just going to keep going for now. Okay, so therefore, let's solve this. Put the C on that side, so it'll be T minus C, multiply it by K, T minus C is equal to log E. Now this is modulus of P, but P is always positive. This population is always positive. You can't have a negative population. Okay, so that'll be just log EP. Okay, so therefore P is equal to E to the K T minus C, or E to the KT minus KC. Now this is all just constants. We've got a K and C, etc., etc. So that's just equal to E to the KT times E to the negative KC. Why am I doing that? Seems like a waste of time. It's because that is just equal to A, some constant A, E to the KT, where A is equal to E to the negative KC. This is all just constants here. E is a constant, K is a constant, C is a constant. That's just all some number. Let's just call it A and be done with it. It's a lot simpler to deal with. And you'll see why now about how this question gets a lot simpler. Okay, just try to give myself a bit of space. Now we've got two constants to be able to find. We need to know A and we want to know K as well. Okay, so let's put this in. Firstly, this initial condition is the easy one. When t is equal to 0, you can see that that's going to be easy. So therefore, population is equal to 200 when t is equal to 0. So that'll be equals e to the 0. E to the 0 is 1. So therefore, a is equal to 200. And whenever you're solving these types of equations, your initial value will always be a. A is your initial value. So if you get a question that says the population starts at 1500, a will be equal to 1500. It always happens that way. Okay. So this tells us then, putting that in, p is equal to 200 e to the kt. Fantastic. We're halfway there. We just need to find k. Let's substitute the other one in. Now this is where it could be 50-50 depending on your algebra number sort of skills on when you sort of substitute this in. So I'm going to run out of space. I'm going to give it a go. I'm sorry about having to squish this in. Okay. So therefore we also know that the population is 1000 when t is equal to 10. So we've got 1000 equals 200 e to the 10 k. In other words, putting in t as 10 is that. So now let's solve this for k. So therefore, divide 1000 by 200 to get 5 equals e to the 10k. So therefore, k will be equal to, if we take the log of that side and then we divide by 10, you get 1/10 log e of 5. That's what k is equal to. Which looks horrible, and it is. But when you get used to this, it's actually not that bad. Let's now substitute that all back in and see what we get. So therefore, to finish off, we've got the population is equal to 200. Let's write it out in full. E to the power, k is 1/10 log e 5t. Okay, so that's just times 5. Okay, now let's just simplify that a bit. That's equal to, rewrite it a little bit, 200e. Well, we like this bit. We like the fact that that's log e5, and I'll just do that because if we raise that to the power 1/10 times t, so just rearranging the order of that, it looks a lot nicer, doesn't it? Because what's e to the power log e5? That's just 5. So that's equal to 200 times, this is 5 to the power 1/10 times t, which is just t over 10. And that is your particular solution. Okay, I'll just rewrite that. P equals 200 times 5 to the power t over 10. And that is your general solution that predicts the population growth of rabbits at t years. So there you go. Make sure you follow that. You'll be doing that process so often. It's just good to get used to this stuff down here. Dealing with those constants can sometimes be a nightmare. If you're finding it a nightmare, you're probably doing it the wrong way. Go back and try a different way, and you'll get used to knowing which way is the best. Have fun. I'll do some multiplications in the next video.